In this video, I'm going to discuss immunogenetics and the work I've done with immunogenetics. Welcome to the Art of Breeding with Brian Reeder. First, let's define what immunogenetics actually is. As the name implies, it is a branch of genetics that deals with the immune system, or immunity. However, I want to be clear that it's not immunology. I've had discussions with various people over the years who come away from it and think, oh, it's just immunology. Well, it's not exactly. To define the word, immunology is the study of the immune system in all organisms and how it functions in both health and disease. It is a branch of biology and medicine. Immunogenetics, though, is slightly different. It is the study of how genetics and the immune system interact. It is a branch of medical genetics and medical immunology. Okay, but I want to be very clear that I did not come to my work with immunogenetics because I was interested in immunology or because I was trained in immunology. I came to immunogenetics because I had a problem that I needed to solve. And so I began doing research. And the first place that I turned in that research was to Fred Jeffries, who I had known as a child, who was a scientist and a poultry breeder. He was a poultry scientist, poultry geneticist. I turned to some of his books that I still had at that time as an adult. I believe it was in his book Bantam Chickens. I keep coming back to, I think it was in the book Bantam Chickens, but it may have been one of his other books. But anyhow, he says, open the chicken house, let the wind in, let the birds be exposed to nature, let them get sick, get rid of the sick ones, keep the strong ones, only breed from the ones that don't get sick, and that'll take care of your problem. And of course, that is the layman's way of looking at immunogenetics, because what you're wanting to do is find those resistant individuals and breed from them. So that was the first thing I turned to. And then I thought, okay, Jeffries was not just, chicken breeder from up a holler who had dreamed up some fantasy that you could do this. This was a trained scientist who I knew as a child, who I knew was well-versed in the sciences and wasn't just making up a story. So I then went from Jeffries and started practicing what he recommended in my poultry house. And then while I was doing that, I began to start to search the literature. One of the most important sources was Crawford's book on poultry genetics. It's one of the standards. It's a big, thick textbook. And I found a lot more information on genetic disease resistance in that book. I began to realize that there was a difference between acquired immunity and genetic immunity. And acquired immunity is fine, but it doesn't necessarily pass to the next generation. What you really want is genetic immunity, which allows you to breed a line of animals or plants that show the resistance for the pathogen in question that you're dealing with. In poultry, where I did this work first, I was dealing with two pathogens, Mycoplasma gallisepticum and the Marek's virus complex. Now, it just happened to turn out that with these two pathogens, the genetic resistance, the actual genes that gave them resistance to these problems, to these pathogens, occurred on the same locus of the chromosome. So that means they were alleles at the same locus. That also meant you could not have them both homozygous at the same time. So I had birds that I had selected that were homozygous for Mycoplasma, but were not homozygous for resistance for Marek's. They were resistant for Mycoplasmas, but were not resistant to Marek's. Or they had very mild resistance, because there are also modifier genes that affect these major genes. And if you just have the modifier genes, you may see mild resistance. But I wasn't seeing the kind of high resistance that I saw with Mycoplasma in the birds that were homozygous for the genes for Mycoplasma. for this resistance gene, and maybe the modifiers as well. But in time, I found an individual male chicken, a rooster, that was resistant for both Merrick's and Mycoplasma. And I knew that chromosomal realignments could occur in meiosis, and that unless you were looking at pleiotropy, there was always the possibility that a tightly linked gene or even an allele at the same locus could jump to a different spot in the chromosome and move, find a new locus at which to reside. So in this bird, in time, I would come to learn this is what had happened. But to begin with, I just simply observed this in this bird. When you have full homozygosity for either of these genes, you basically see immunity. There's a difference between immunity and resistance. But first, I just want to give you this little story. So, in test mating this bird, he was immune to both Merrick's and to the Mycoplasmas, and he could produce offspring when bred with my birds that showed the immunity, the high resistance immunity to mycoplasmas, but did not have the strong immunity to the Merrick's viruses. When he was crossed into those lines, he was producing birds that had the high immunity to the mycoplasmas, but he could also then produce offspring in later generations, because both of those genes are recessives, that showed the high resistance for Merrick's virus, for that complex. There's multiple forms of it, but the resistance is the same, at least in all the instances I've worked with. What this turned out to be was an actual chromosomal realignment. But at the time, I didn't know that, although I suspected it. What I did know was that this bird had breeding value for the traits of resistance, immunity for mycoplasmas, and resistance immunity for Merrick's virus. And he could pass this to his offspring. So this was not an example of acquired immunity, nor was it an example of something that was just a false immunity. This was the real deal. Now, that's the work I did in chickens. And over time, as I bred the lines that had the most immunity, I was able to intensify that until I was seeing that not stronger in the individuals, but stronger in the lineage, which told me that this was something multigenic. It was behaving in a quantitative manner. In those earlier generations, I was not seeing the higher percentages in every generation that I would come to see later. It gradually took a few years, a few generations of selection to get them to the point where I was seeing 80 or 90% of the offspring showing this seeming high immunity. And I was exposing them. I was doing blood sampling, so I knew that they were carrying these pathogens, and periodically they were being exposed to birds that were symptomatic, because I was also outcrossing these lines to symptomatic birds to study the segregation of the genes. So I knew over time what was happening here, that this was not just these simple single genes. They gave seeming immunity to a certain amount of the flock, initially about 10%. And then within a couple of generations, about 30%. And then within a few more generations, about 60%. And then on up, finally, I had them to about 90%. And even the birds that would break down and show some symptoms were quite mild. So I was not seeing the extremes of susceptibility anymore. That was gone. And I believe if I continued on with that line, I probably would have been able to get them at 100%. However, I was not able to. I didn't just quit. A weasel wiped me out, and that was it for that line. Or for the lines, there were several of them, for the 5 lines that came out of that breeding. But anyhow, that's a whole other story. I had this long period of working this immunity selection, and this is immunogenetics, because this wasn't a matter of just dealing with the immunology. It wasn't a matter of dealing with their immune system. It wasn't a matter of working with birds with acquired immunity. It was an example of working with birds that actually had the genetic immunity, so that you could breed it and perpetuate it and create a line that showed it and that could be intensified so that they had more and more and stronger immunity across the line. And this also is a wonderful example of dealing with quantitative multigenic traits, because what I believe was going on there and what our sampling seemed to indicate was that in addition to the major genes, there were a body of minor genes that supported and intensified the results the more homozygous they became, and the more of those were present in a homozygous state. That's immunogenetics. Now, in the daylilies, I have pursued this work there as well, because there are two issues that are similar to somewhat the same in the daylilies. In the daylilies, the two versions of this are rust, which is a fungus, and thrips, which are an insect that feed on the daylily flowers and the scapes as they're forming. And this causes a lot of problems. Now, that's not immunogenetics. This is not a matter of having immunity to a pathogen. The rust resistance is. The other is something similar. It is selection against pests, against susceptibility to pests. And I believe there are different functions going on there. I'm sure there's a genetic basis to that. I'm certain of it, because I now know how thrips resistance works genetically. It's a recessive trait, and it also can be intensified, so it can clearly have modification by more than one minor gene. But it is not exactly immunogenetics in the same sense that the rust resistance is. Rust is a pathogen that gets into the plant and lives inside the organism. The insects don't live inside the organism. They're just coming and feeding on the organism. They're a parasite. Yet both are selected in the same way. The plants have to be exposed to rust or thrips to select for rust or thrips. You have to have exposure in order to do immunogenetic selection. Then once you have the exposure, you can go through and you can find the individuals that show the least amount of the problem. And what you really want are the individuals that show no problem even when they are fully exposed and you know they have been inoculated. So with thrips, the flowers that never show spots and streaks, and the buds that never show rough texture and knobs and spikes and thorns and horns, those are showing immunity to the thrips. And what I look for is during a thrip outbreak, especially in dry periods, the plants that have the smooth, clean buds and the flowers without the spotting and streaking, while thrips are visibly crawling on them. I have some theories as to why thrips would want to feed on one plant and not want to feed on another. I don't want to go into those because I've not proven any of that out, and I don't know that that's true, and I don't want to put it out there and have people repeating it like it is true. But let's just say there's something, and it's genetic, it's heritable, that makes certain plants unpalatable to the thrips, to the parasites. Now, this can clearly happen with other insect pests as well. I know people who have problems like this not with thrips, but with aphids or with spider mites. Although with spider mites it manifests a little differently, but with aphids you can see almost exactly the same problem. And you select the resistance to that problem in exactly the same way, and it may even be the exact same gene. Whatever's making the flowers unpalatable to the thrips is probably what's making the flowers unpalatable to the aphids as well. Now, with rust resistance, that's different in the sense that the rust is inside, and it's more like immunogenetics. Now, in the poultry, I never saw an instance where the resistance failed. That is, even when I brought in birds that were known carriers of the pathogens, I never saw an instance where there was enough of a mutation in the pathogen that it could break the boundaries of the resistance and infect the birds. But in plants, it doesn't always work that way. Even in animals. in almost any situation, resistance can fail because the pathogen can evolve a way to breach the boundaries of the resistance genes. But I never saw that in the chickens, though I would have in time if I'd carried on long enough. In daylilies, rust is constantly evolving. The rust pathogen is constantly evolving and creating new strains. And so you can see something that was super resistant encounter a new strain of rust and show some susceptibility, become less resistant. However, I have never seen an instance where a daylily that was seemingly immune, or what I call A+ level resistance, suddenly encountered a new strain of rust and went to like C or D or F level. The worst levels, what we would call in the hobby a rust magnet. What I have seen is like an A+ go to an A or a B. An A or B is not bad. That's still resistance. So I think what happens in most instances with these rust pathogens is that the new pathogen that can breach the barriers of the resistance still can't breach it fully. In other words, the resistance genes there still provide some resistance. And what makes me think that is even things that were found to be resistance back in 2000 when rust first entered the U.S. So something like Bela Lugosi, that's been known to be resistant from the beginning, was more resistant at one time. But even now, it still shows moderate resistance, B level, and it is still a useful breeder for rust resistance. Now that brings me to one other little thing that I want to point out, and that is that the way you want to breed for rust resistance and the way you want to breed for immunogenetics in general is a quantitative process that I call gene pyramiding. Well, I don't call it that. That's what science calls it. Gene pyramiding is where you bring multiple genes doing the same thing together in one organism. Now that is what was happening in the instance where I had the major gene for Merrick's and mycoplasmal resistances, and then I kept selecting and they kept getting more and more resistant as a population. That was a form of quantitative multigenic selection. Not that I was bringing together multiple major genes, but that I was bringing together the major gene and multiple minor genes that I was bringing to homozygosity for as many of those together as possible. In gene pyramiding for rust and daylilies, you want to bring together as many major genes and minor genes as you can find, because my research and my screening program and then breeding to prove breeding value for rust resistance within those that screened high for resistance showed that there is more than one gene for resistance. There are some recessive rust resistance genes and one or more dominant rust resistance genes, and they all don't show the same level of resistance if it's just the one gene. I did find certain plants carried this super strong dominant resistance gene, and the two plants that seem to have that is ancient elf and Himmercalis fulva Korean. Those are the two strongest rust-resistant plants I ever found, and I suspect maybe some of the full siblings to ancient elf might have that also. Certainly the couple that, the 3 or 4 that I had also did, but they had much worse thrips susceptibility, and I didn't like the plants as well, so I didn't do the long screening with them to be as certain. But they probably would have been just as rust resistant, because they would have been the same family line, or at least close. But for me, Ancient Elf and Himmercalis fulva Korean were the two that shown the highest resistance. Now the O'Leary fertile form of the fulva and the hand cow seem to also have similar, very high resistance. Sempervirens also seem to show very high resistance. Vespertina also seems to show that very high resistance. But again, I did not breed with them so extensively. The ones that I had the experience with, both for their visible resistance in the field after inoculation and their breeding value, that's Ancient Elf and Himmercalis fulva Korean. So from observing those, I was able to note this really powerful form of dominant resistance. When it was added with other forms of resistance, when I would cross them to other daylilies that also showed resistance but clearly was one of the more recessive forms or a dominant with lower penetrance, then I was seeing instances where I would get even stronger resistance in some of the offspring. A good example is Ancient Elf crossed to Solaris Symmetry. Ancient Elf showing the super high dominant gene, Solaris Symmetry showing a mildly penetrant dominant gene, and probably carrying one or more of the recessive genes. When those two were crossed, there were probably 85 to 90% of the seedlings showed super resistance. The rest showed high resistance. And out of that super resistance, a percentage of them, and a pretty good percentage, probably as many as 30 or 40%, showed immunity and kept it through all 5 years that they were tested. Now, that's exceptional. I saw the same kind of thing out of Hemerocallis fulva Korean. And so what I did was work to stack those recessive, mildly penetrant dominant, and dominant resistance genes together. And now I know which lines come from which plants and what they're potentially carrying. And even though I'm not selecting for rust resistance, it's always in the back of my mind. All my base plants have a known quantified provenance for their rust resistance. And I'm able then to think about that as I'm making my crosses and combine them in such a way that even though I'm not doing selection, I'm still trying to bring together as many resistance genes as possible. And then I also ship my introductions to the South where rust is an endemic issue. And from that, then I can get feedback from other people. So it's a more passive form of resistance breeding. I know that I have this resistance base. I'm not actively selecting, which is what I would have to do. I would have to have the inoculation exposure to be actively selecting. But I know, because it's on every side when I make my crosses, that I'm bringing those genes together. That is what then, when the plants go out into other gardens and I get feedback, then I'm selecting for the rust resistance. With the thrips resistance, that is active. I'm actively doing that work because that is a problem in my garden. Immunogenetics is selection for genetic resistance, and it's the most powerful kind of resistance. This is a short video, so I'm sure I've not covered it in the depth I would like to, and we'll keep coming back to this issue in future videos. But for now, if you have any questions on anything to do with this subject, or things you would like for me maybe to touch on in a future video, just leave that below, and I'll see you in the next one. Thank you for visiting my channel. I hope this video was interesting to you. If you would like to know more about this subject, leave a comment or question below in the comments section. Please leave a like on this video and subscribe to the channel. Click the bell notification to be alerted when new videos post. You can find my poultry books on Amazon at the link below in the show notes. My daylily website, sundragondaylilies.com, offers information on booking me for consultations on your specific genetics questions or mentoring for your breeding projects. It also lists all of my daylily introductions, the cultivars that are currently available, and links to my blog where you can find the bulk of my daylily writing. Thank you for joining me for this video, and I hope you'll be back for more. Have a great day.